So this is a short video about the Cantor set. Just as a quick recap, when we first started talking about integration, before we introduced the Riemann integral, I gave a sort of simpler version of the integral, and I proved that it worked for continuous functions. And then we went on and we talked about the Riemann integral, and we developed the theory of the Riemann integral. And I think there's a question which has been lurking for this whole time, which was, did I really need to go to this more complicated version of the integral, or could I have kept with the simple thing? Now, we've seen a few examples where the simple integral doesn't work exactly as written. So, for example, there might be a finite number of isolated discontinuities, but that still might sort of have this nagging feeling in the back of our head that I probably could have done a small tweak. I didn't need to go all the way to the more complicated Riemann integral. And so I wanted to at least present one example, which is, to me at least, somewhat convincing that the Riemann integral is really helpful. That is, it's giving you the answer, the definition for integrals that don't really have an obvious definition. So in order to get there, I need to find a new function, and the function I'm choosing in this video is based on something called the Cantor set. Okay, so here's the Cantor set. It's going to be defined recursively. I let C1 be the whole interval from 0 to 1, and I let C2 be the interval from 0 to 1/3, union the interval from 2/3 to 1. And I'm going to write that in a funny way. It's 1/3 times C1, union 2/3 plus 1/3 C1. What do I mean by that? Well, if I have a set S, say in R, and a point A in R, then the set A times S, I define to be all numbers of the form A times little s, where little s is an element of big S. Okay, so in particular, 1/3 times C1, 1/3 times this interval, is just the interval from 0 to 1/3. I define an addition of sets in the sort of the obvious way as here as well. A plus S is all elements of the form A plus little s, where little s is in big S. Okay, so that's a piece of notation we haven't really used much so far, but it's useful when defining sets in this way. So let's draw a picture. What is that doing? When I go from C1 to C2, I'm taking C1 and I'm making two copies, one here and one here. I'm shrinking both of the copies down by a factor of 1/3, and then I'm moving the second one over to the right. So I make two copies, I shrink them, and I move them. So this here is a copy of C1 but shrunk, and this here is a copy of C1 but shrunk. To make C3, I'm going to do the same thing. So in algebra, it's 1/3 C2, union 2/3 plus 1/3 C2. And in the picture, I take all of C2, which is two pieces, and I shrink them both. I shrink them, make copies, and then move the copies down here. Okay, great. So that's C3, and in general, Cn is going to be 1/3 Cn minus 1, union 2/3 plus 1/3 Cn minus 1. Okay, so again, at every step n, I'm taking two copies of the previous step, shrinking them by a factor of 1/3, and then translating the second one to the right-hand side of the interval. And I define C to be the intersection of all of the Cn's. Now, if you look at this picture, you can sort of see that C1 contains C2 contains C3, and so on and so forth. Okay, so that's my Cantor set. It's this weird looking thing, right? You can see that at every stage it seems to be getting smaller and more complicated. There are more intervals in every stage. And I'm going to define my function f of x to be the indicator function that x is sitting inside of the Cantor set. So my first claim is that f is in fact Riemann integrable. How am I going to prove that? Well, I need to give you a sequence of partitions, and it shouldn't be terribly surprising. My sequence of partitions is going to be very closely modeled on my sets Cn that I'm defining there. So I'm going to let P1 be 0, 1, and that's just the boundary, which I denote by this funny symbol of C1. I let P2 be the set 0, 1/3, 2/3, 1. That's the boundary of C2. And in general, I'm going to let Pn be 1/3 of Pn minus 1, union 2/3 plus 1/3 Pn minus 1, and that's the boundary of the set Pn. Okay? So in other words, I'm sort of exactly slicing off the interesting stuff that's going on inside of Cn. Okay. Well, since I've defined my partitions to exactly match the boundaries of Cn, you can see immediately that this upper envelope function, which I've been denoting f sub u comma Pn, is exactly the indicator function that x is in Cn. Okay. Well, Cn is just a finite union of intervals. So the integral of fu Pn, that's just the total length of the sum of the lengths of the intervals of Cn. So what is that? Well, I'm going to use my recursion formula. The size of Cn, that is, the sum of the lengths of the integral of Cn, is, well, given by the size of this set here. That's just a definition of Cn. But I can see that I have this union of two intervals, of two parts here, which are clearly disjoint. And so the total length of this whole union is equal to the length of the first part plus the length of the second part. Okay, makes sense, right? I have the first part between 0 and 1/3, and the second part between 2/3 and 1. And so the length of the whole thing is just the length of the first part plus the length of the second. All right, but when I multiply a set, then the same thing is going to happen to the length of the interval, right? I have the interval from 0 to 1, and I take a 1/3 times that interval. Well, that gives me an interval of length 1/3. So I can pull out the constants here. And so when I do that, what I find is that the length of Cn is 2/3 times the length of Cn minus 1. Okay, but that's true for every n, so I can do recursion here. And I find, therefore, that the length of Cn is 2/3 to the n minus 1 times the length of C1. That's just 1, because it's the interval 0, 1. And so I find the length of Cn is 2/3 to the n minus 1. Let's put all of that together. My upper bound u of fpn associated with this partition was the integral of fupn, which is just the length of Cn, which I've just computed, to be 2/3 to the n minus 1. And it's clear, of course, that that goes to 0 as n goes to infinity. On the other hand, f is non-negative, so of course my lower bound function is certainly bigger than or equal to 0. And so my upper bound is going down to 0, my lower bound is always bigger than or equal to 0, and so in fact, we check that the integral of f is equal to 0. Okay, so f is in fact Riemann integrable. The next thing that I want to check is that f in some sense is really, really hard to deal with using a naive theory. Now, that's not a mathematical claim, but one mathematical claim that's certainly related to this is that f has uncountably many discontinuities. So that's a weird looking function, and in particular, it's a sort of function that you're not easily going to be able to tame using a very simple notion of an integral. So how do I check that? Well, I need to make the following sort of weird looking observation. I'm just going to explain what's going on here, and if you care to do so, you can pause the video and work out the example for yourself and work out a few particular numbers. But if not, you can just accept that the following is true and something that's not very difficult to check. So here's something that we certainly already know. If I have a number x between 0 and 1, I can write down the decimal expansion for the number x. That is, I write something like x is equal to 0.a1, a2, a3, ... where these ai's are integers between 0 and 9. And when I write something like this, that's really shorthand for writing that x is equal to the sum over all the natural numbers j of aj times 10 to the minus j, right? These are really the same thing, right? Okay. It shouldn't be terribly surprising that just like we have a decimal expansion where I have a 10 here and the aj's are less than 10, you can also write down binary expansions and indeed ternary expansion. So I can write x is equal to sum j and n of aj times 3 to the minus j, where aj is between 0 and 2. Okay, so it's exactly the same thing as decimal expansions, except I'm expanding things base 3 instead of base 10. Why did I bother to do any of that? Well, here's the claim. The Cantor set C is exactly the point x that has ternary expansion, where all of the coefficients, these aj's, are 0 or 2. So that is, there are no 1s in the ternary expansion of C. Okay, so that's something that you can check for yourself. It's almost immediate from the recursive definition of Cn. Okay, great. What are some consequences of this way of writing down the Cantor set? Well, the first immediate consequence is that f is discontinuous at all points in C. How do I check that? Well, I just have to check that f changes quickly for every point x in C. So I'm going to fix a point x in C, and I'm going to write down its ternary expansion. Next, I'm going to fix epsilon greater than 0, and I need to find a point that's within epsilon of x, for which f of x is quite different from f of y. So how do I do that? Well, there certainly exists some natural number n, so that 3 to the minus n is much less than epsilon. And then I'm going to find my new point y to have this ternary expansion b1, b2, and so on, where bj is equal to aj for all j's except for n, and for j is equal to n, I let bj is equal to 1. Okay. So because y has an element besides 0 and 2 in its ternary expansion, we know that y is not in C. On the other hand, the only place where they disagree is in the nth coordinate, and so x minus y is exactly 3 to the minus n in absolute value, and by assumption, that's less than epsilon over 10. Okay, so f of x is discontinuous at x because I found a point y that's very close, for which f of x minus f of y is equal to 1. Great. So f of x is discontinuous there, and then the next claim is that C is in fact uncountable, and I can actually give a bijection between C and the closed interval 0, 1. And here's the bijection. If I write down the ternary expansion for x here, for a point x here, then I can map that to this point here, sum of aj over 2 times 2 to the minus j, and I note that that's actually just a binary expansion, right, of a number x in the interval 0, 1. And because aj here is either 0 or 2, you can immediately see that in fact every binary expansion of a number in 0, 1 is of this form, so this really is in fact a bijection. Okay, let's put together all of the things that we did in this video. We defined this set C and this function f that was just the indicator function that x is in C. We checked that f is Riemann integrable, and indeed we even calculated the integral, despite the fact that this function f has uncountably many discontinuities. It's discontinuous at every point x and c itself is uncountable. All right, so that's sort of nice. We have this weird looking function, but we can use the fact that we have a lot of flexibility in defining the Riemann integral, and in particular in choosing really nice partitions, as we did here, to actually calculate the Riemann integral even for this weird looking function. Thanks.